First of all, the usual advice applies here. If they don't give you a picture, draw a picture and read the question carefully. Beyond that, there's a whole bunch of stuff about parallel lines that I need to explain to you guys. So, you're going to see a lot of situations where there are parallel lines and other things drawn in there. For example, what they call a transversal, which just means line that crosses both of them. Any line that isn't parallel to two other lines, let's say you have two parallel lines. Well, there's only two ways to draw a third line. Either it is also parallel, or at some point it's going to cross them. So, woohoo, transversal, other line that isn't parallel to the first two. Yeah, here's the symbol for parallel, a filled in arrow, although sometimes I don't bother filling it in. Facts about transversals and parallel lines. This intersection is basically a mirror, a carbon copy of this, a photocopy I should say, because I don't live 20 zillion years ago. I'm only way out of date. Photocopies. Yeah, so these angles, since these intersections are exactly the same, these two angles have to be the same. The word for that officially is corresponding angles. But if those two are the same, that also means that this is the same as this, as the same as this, is the same as this. Because angles opposite each other at intersections like this are always congruent. This is the vertical line theorem. You can ask somebody, but it's pretty obvious that these two are exactly the same. And once you know that, it actually turns out that these four also have to be the same. And since these two add up to 180, because together they make a straight line, that means this is the same as this, but it's the complement of that. The supplement of that, they add up to 180. And it makes for a lot of like, oh, if this is this, then this has to be this. And that's what math team is full of. Let me give you one example here. People have told you that the triangle's angles add up to 180 degrees, as was demonstrated earlier, but no one ever stopped and explained why that has to be true, right? Like, we know that a straight angle is 180 degrees, but what is it about triangles that make them exactly the same as a straight line? Well, I'm going to show you something. Here I have a triangle in between two parallel lines. We know nothing about any of these angles, but I'm going to prove to you that a straight line has the same number of degrees as a triangle. Consider this angle over here. Let's call it angle A. Here's a transversal through these two parallel lines, right? Can you find another angle that has exactly the same measure as angle A? I'll find it for you. It's here. Actually, it's also over here. These are corresponding angles. They're in the same position in those two intersections. I notice that I'm basically ignoring this line here right now because we're only caring about this line's interaction with these two lines. It looks like it's a little bit more than 90 degrees. This looks like it's a little bit more than 90 degrees. They're both 90 degrees. Now, consider this angle over here. What angles are the same as that? Well, this one over here, yes. But over there, notice this intersection is the same as this intersection here, so this is the same as that. Actually, this one's also the same, but I'm not going to bother marking it. And now take this angle, C. Right? Take a look at these three angles. A, B, and C together make the number of degrees in a triangle. Over here, A, B, and C also make the number of degrees in a line. So the number of degrees in a straight line, 180, has to be the same as the number of degrees in a triangle because they're made out of the same total number of degrees. Whatever angle A is, whatever angle B is, and whatever angle C is. It has to add up to 180 because they do here, so they have to over here. Any triangle adds up to 180 degrees, one additional proof of it. And basically this is full of problems involving getting around parallel lines. Let's see if I want to do an example here. Oh, now I want to point out a whole bunch of other facts first. Parallelograms. take a parallelogram, which has a parallel line with this, and a different parallel line here and here. If we extend this side, and extend this side, and extend this side, now you can see why these angles have to add up to 180. Because this angle is the same as this angle, they correspond. So this is what I mean by extending some sides and then you can see things. And then this is supplementary to this, they add up to 180, so this adds up to 180 with this because this is the same as that. Different factoid about parallel lines. Here's a line, here's a parallel line. We declare them to be parallel. Let's say that there's a third line here. This is 3 inches, this is 4 inches, and this is 7 inches. This, and that. What does that tell me? Well, since it widens at the continuous rate, that tells me that whatever this distance is between the 3 inch and the 4 inch, this has to be 3 times longer. Alright? There's proportions at work here. If this was exactly 5 inches, it would have to be exactly halfway between the 3 inch and the 7 inch, because it gets, here it has no width at all, and then it gets wider and wider at the same rate the whole way down. Side fact, let's say I drew a parallel line here, and I told you it was parallel. I mean, there's weird things you can do if they're not parallel. You can make it longer or shorter or whatever. And I told you this was 2 inches, and this was 4 inches. Well, now you know that whatever distance this is, this has to be twice as big. So whatever the gap between 7 and this mystery number, it's twice as big as the gap between x and 3. So you would take the entire gap between 3 and 7, which is 4 inches, and you'd cut it into a 2/3 part and a 1/3 part. What's a third of the 4-inch gap? Well, that would be 1.33 inches. So this has to be 1.33 inches longer than this, and this is to be 2.666 inches less than that. So that would be 4.33 bar inches long. You can do stuff like that with parallel lines because it grows at a uniform rate. Yada yada yada. I won't get into it. Basically, sometimes you can rely on instinct there. All right. I'm gonna try to do a problem on air. Not from last year, because last year there were a lot of problems that were not so good, and in the end it didn't turn out to have solutions. But from one before that. Oh, I like this one. From 2013, problem 2. They give us a diagram with 2 parallel lines. And they tell us that these lines are parallel. And then they ask us to compute measure of angle MCL. And they tell us Y in C is 39 degrees. And they tell us CLA is 57 degrees. And they want to know this. Alright. In situations like this, it usually helps to draw a third parallel line. Again, you can add stuff to the diagram. Well, not again, I mean, you can add stuff to the diagram. So what does this tell us? Well, if this is 39, then this is 39, because those are parallel lines, and those are, well, if you extend this is also 39, and this turns out to be corresponding to that. There's a situation here, alternate interior angles, that's what it's called. Over here, same thing, 57, 57. So you can just add the numbers together, and you get, what is that, 96 degrees. Woohoo, that was a quick answer. That was easier than I thought. But yeah, basically you can draw extra parallel lines if you want to, somewhere where it's convenient to help you see the comparisons there. I think that's everything I need to point out.